Well, hey, everybody. What we're going to look at here in this recording is sequences. And basically, a sequence is just a list of numbers. There doesn't even have to be any reason to the numbers. Even a random list counts as a sequence. Now, very often, your sequences do fit patterns, and those are the types that we're going to be looking at most closely. So let's start with these that we have here. So if you take a look at your screen, notice that there's a number here off to the side, 5-42. Whenever you see something like that, that means that this comes from your textbook. So if you look in the materials, you'll see the unit number listed, 5.2.1. I know that's a lot of decimals. But then this problem, 5-42, comes from that section. So you can always look into your textbook to follow along if you like. Here's what I would like. Take a moment. I'd like you to pause the video and then only unpause when you're ready to check. I want you to, as much as you can, see if you can figure out what the pattern is that's going on here. Now, there are multiple patterns that could fit these, but there is one that is the simplest, and that's what we're going for here. What's the simplest pattern that's occurring in these numbers? So for each list, you're going to start at the front and work your way to the right to see if you can figure out how you are getting from one number to the next to make a prediction. So at this point, pause the video, find the next term, the next number in the sequence for as many of these as you can. Okay, I hope very much that you did that pause. I'm going to now share with you what I had for my next numbers in the sequence. Let's see how you match up. So here I had an 8, a 16, 13, 6, and 32. And then over here, a 24, an 8, a 1. Then this is the fraction 1/3, and then a 20 going on. Okay, we'll talk in just a moment here about where all those came from. So if you're not sure, that will be coming here in just a moment. So of these, there are two particular types that are more useful, a little more common, and those are the ones we're going to focus on today. Here's the first. When a sequence generator, all that means is when the pattern of the sequence is that you add the same number to each previous term. A term is just referring to the number in the sequence. So the first number is the first term. The second number is the second term, the third term, the fourth term, etc., etc. So when you add the same number each time, you get what's called an arithmetic sequence. So taking a look at this same list, I'm actually going to go back to the previous page. I want to know in which of these the simplest pattern that we found is simply that we add the same number every time. So let's take a look at the first. From -4 to -1, if you're adding a number, that's going to be, what, a +3. So a +3. To go from -1 to +2, that would also be +3. To go from 2 to 5, that would also be +3. To go from 5 to 8, that also, we're just doing a +3 every time. That's what an arithmetic sequence looks like. So right away, we know that sequence A, which has a common difference, it's called, we added 3 each time. Now, I think I am going to stay on this page now. Does the same thing happen here? To go from 0 to 1, you add 1. To go from 1 to 4, though, you add 3. Those are not the same number. To go from 4 to 9, you add 5. Yeah, so we're not adding the same number every time. So letter C here, excuse me, not an arithmetic function. Next up, to go from 1 to 1, you'd add 0. From 1 to 2, you'd add 1. Okay, already we're not adding the same number every time. So that's not arithmetic. From 48 to 24, now you're going down, so you'd be adding a negative number, but that's okay. Do we add the same negative number to get from 24 to 12, though? No, there we'd only go down by 12. So we're not adding the same number each time. G is not arithmetic. Looking at I, From 8 to 2, we'd add negative 6, but from 2 to 0, you'd add negative 2. Those are not the same number, not arithmetic. Take a look at B, from 1.5 to 3. Okay, so from 1.5 to 3, you need to add on another 1.5. From 3 to 6, you'd add on 3. Okay, so already we're not adding the same number each time. That is not arithmetic. Okay, letter D, from 2 to 3.5, you're adding on 1.5. From 3.5 to 5, ooh, there you're also adding on 1.5. And from 5 to 6.5, also adding on 1.5. This one fits, and that's why the predicted next number of 8 is just what you get when you add on a 1.5 to the 6.5. So another arithmetic one was sequence D, where we added 1.5 every time to get to the next step. Letter F, from 9 to 7. Now it goes down, so you're adding a negative number, but that's okay. It's a negative 2 that's being added. 7 to 5. Again, we go down by 2. 5 to 3, down by 2. Okay, this looks like an arithmetic pattern. That's why I made the prediction the next number was 1, which took us down another 2. So letter F, where we added a negative 2 each time, also arithmetic. Okay, and I just want to remind myself here that we decided this one was also arithmetic. Letter H, 27 to 9, you've gone down by 18. From 9 to 3, you go down by 6. Okay, it's not the same difference every time. Now here with the fractions, don't make it tough on yourself. When you do the difference, you're just taking the back number minus the front. So the second number minus the one in front of it. So I'm just going to pull up my calculator quick. Do 5 divided by 2 minus 5 divided by 4. And the difference is 1.25. So let's see. If I do the same thing here, do 5 minus 5 over 2. Do we also get 1.25? Minus 5 over 2. Let's try 5 over 2. Nope, it's not the same difference. Not the same number. So this one also not arithmetic. So our arithmetic ones are A, D, and F. So which fall into this family? A, D, and F. Should we include F? Yes, because you can add a negative number. If the numbers get bigger as you go down the list, then you are adding a positive number each time. If the numbers get smaller going down the list, just means you could be adding a negative number. That's okay. So that's one main type of sequence. Here's a second main type, and it is called the geometric sequence. Now, the geometric sequence, rather than adding the same number each time, you are multiplying by the same number each time. Let's take a look at how you investigate this. So in the case of, well, we haven't looked at, let's go in alphabetical order this time. So we did A already, B. To go from 1.5 to 3, how much do you multiply by? The way you check that is by doing a division. Take the back divided by the front. So do 3 divided by 1.5. Okay, it's a multiplier of 2. So I'm going to go back to here, multiply by 2. To go from 3 to 6, that one's a little easier, multiplying by 2. To go from 6 to 12, multiplying by 2. So let's continue that one more time. That's where the 24 comes from. And we're just multiplying by 2 each time. So B is geometric because we're multiplying by 2 to get from term to term. Okay, letter C. Well, here there's a big problem because if you multiply 0 by any number, it's going to stay 0. It's never going to turn into a 1. So right away, we know letter C is not a geometric sequence. It's something else. D we know is arithmetic. Let's check E. So to go from 1 to 1, you multiply by 1. To go from 1 to 2, you multiply by 2. Okay, already it's not the same number each time that you're multiplying by. This is not a geometric sequence. Let me get the lights back on here. Thank you for that. The energy saving thought that I wasn't here anymore. Okay. We know letter F is arithmetic. Letter G. To go from 48 to 24, what do you multiply by? Remember the way to check. Take the 24 divided by 48. Let's see what we get. I'm going to clear these out. 24 divided by 48. Multiplying by a half. Okay, so multiplying by 0.5. Is the same thing true here? If you take 24 times 0.5, do you get 12? Let's take 24 times 0.5. And oh, look at that. We do get 12. So this fits the pattern for a geometric sequence where we're just multiplying by a half each time. So half of 48 was 24. Half of 24 was 12. Half of 12 would be 6. Just multiplying by another 0.5. So coming down here, that was letter G. So yes, G is going to be geometric, where we're multiplying by 0.5, or you could write it as a fraction. You can write multiplying by a half. That would work as well. So these are called the common ratios. The common ratio here is 2, and the common ratio here is 1/2. Okay, letter H. Let's take a look what we got. So from 27 to 9, how much do we have to multiply by? I'm going to clear these out again. Remember, the way you find that is you're going to take the end result divided by where you started. So 9 divided by 27. Hope you recognize that decimal. That's the fraction 1/3. So to get from 27 to 9, you multiply by 1/3. Is 9 times 1/3 equal to 3? Sure enough, it is. Is 1/3 of 3 equal to 1? Sure enough, it is. So if you multiply by 1/3 one more time, what we're going to see is 1 times 1/3 means the next number in the sequence should be 1/3. So letter H, also geometric. The common ratio is that each time you multiply by 1/3. Let's continue on. Thanks for sticking with me. So to go from 8 to 2, you'd be multiplying by 1/4. But to turn a 2 into a 0, you need to multiply by 0. Those are not the same number. You're not multiplying by the common ratio each time. Letter I is not geometric. And then lastly, letter J. So from 5/4 to 5/2. Well, let's see. What do you multiply by to turn 5/4 into 5/2? So I'm going to take the end result, 5/2, divided by where we started, the 5/4. Okay, so to get from 5/4 to 5/2, we had to multiply by 2. Let's then check again. To get from 5/2 to 5, how much do you have to multiply by? Well, does multiplying by 2 do it? The 2's would reduce, we'd be left with 5. Sure enough, it does. 5 times 2 again gives me 10. All right, this is the sort of pattern you're looking for in that geometric sequence, multiplying by 2 each time, so that next number should be 20 after you multiply by 2 again. So letter J is also geometric because we're multiplying by 2's. Now it asks here, so which are geometric? These are geometric. Should H be in the group? Yes. Notice that in both G and H, the numbers got smaller as we went, but they got smaller by the same ratio each time. That's all that matters. So whether it's a decimal you're multiplying by, or a fraction, or a whole number, doesn't matter. If it's the same multiplier each time, you have a geometric sequence. By the way, that number can be negative as well. So if you have a negative common ratio, you would see mixes of positive and negative numbers together. So let's summarize this all together. So important stuff. In an arithmetic sequence, each term is separated from the one before it by a common difference. That means you're adding the same number each time. So in this example, you're adding 3 each time. In this example, you're adding -5 each time. In a geometric sequence, you multiply by the same number to get from term to term. So in this example here, the common ratio is -3. You're multiplying by -3 each time. That's how you're moving down the list. In this one, your common ratio is a half. 40 times a half, times a half, times a half, times a half. Now, if you're interested in those other sequences, the ones that were not geometric or arithmetic, stick around. Otherwise, you can be finished here. Okay, so we had 1, 2, 2, 2. So these are all taken care of. 2 of these are taken care of, but letters C, E, and I, we haven't figured out what sort of pattern was going on there yet. For this first one, this is just a list of the perfect squares. So that's a little tougher to see. This is 0 to the second power. This is 1 to the second power, 2 to the second power, 3 to the second power. So the next term is going to be 4 to the second power, which gives us 16. That's where the 16 came from. Now this one down here, we're going to come back to E. Letter I think, is one of the toughest, actually. This follows a quadratic pattern. Here's what I mean. The terms of this sequence follow a pattern of 2 times the term number minus 3 squared. This is what I mean by saying it's tricky. So for example, if you put your first term, so put a 1 in here where the n is, 1 minus 3 is -2. -2 squared is 4. 4 times 2 is 8. That's where that 8's coming from. For the second term, put a 2 in for the n. 2 minus 3 is -1. -1 squared is 1 times 2 is 2. That's where these are coming from. So for this next term, we got 1, 2, 3, 4, 5, 6, 7. The seventh term, put a 7 in for the n. 7 minus 3 is 4. 4 squared is 16. 16 times 2 is 32. So that's how I came up with my number there. So that one, I think, very, very tricky. And this last one, letter E, is actually a very, very famous pattern called the Fibonacci sequence. Now, if you take a look, you actually need to start it with 2 numbers. But then after that, each other number is the 2 numbers in front of it added together. So 1 plus 1 gives me 2. 1 plus 2 gives me 3. 2 plus 3 gives me 5. 3 plus 5 is 8. So the next one's going to be 5 plus 8, which takes you to 13. So these here that we just looked at in green, they're fine sequences. There's nothing wrong with them. They're just not geometric and not arithmetic. So we would classify those as being neither arithmetic or geometric.